Yeah, so I'm going to be talking about our newest paper, No Zero Shot Without Exponential Data. And a quick shout out to all the folks. I worked on this project with across a bunch of institutions, Cambridge, Oxford, Tübingen. Um, and yeah, so to dive in, I'll just start quickly with a very simple question. What is generalization? In the olden days of classical machine learning, we used to have a very simple setup, right? We had a small training set, we used to fit a model, and then we used to evaluate that on a held out test set. And we knew exactly what the training set contained. It was small scale and controllable, and we knew what was in there, right? Because we could manually inspect some of those samples. Similarly, we knew what was in the test set, and this was usually held out. So you could manually inspect if there is an overlap between the training set and the test set or not. And the assumption is usually this would be totally unseen, right? However, as we started coming towards the 2020s, training sets started getting bigger. And obviously annotating them started getting costlier, right? So people started thinking about other kinds of generalization beyond just the standard train test generalization. And they call this zero-shot learning or zero-shot generalization. So the premise of zero-shot generalization, very nicely articulated by this paper, is essentially that you have a bunch of classes during training time, and the testing classes that you were going to see are totally going to be disjoint from your trained classes. So the premise essentially being that could you learn a bunch of attributes during training your model that you could apply at test time without actually knowing the exact classes from training. So sort of a simple example would be something like you would learn about a bear and you would learn about maybe a wet apple, and then sort of the, I guess, easy test time example that you would want to generalize to is like a wet bear or things like that, right? So essentially you would want to look at attributes rather than classes themselves. And then in 2021, the CLIP model came with a big bang. And if you actually look at the abstract in their blog post, the term zero shot very saliently stands out, right? Similarly, in figure one of their paper, you can clearly see that they mention the term zero shot multiple times. And actually, I did this math, and the term zero shot is mentioned 201 times throughout the CLIP paper, right? However, the actual way they do zero shot classification that they call it is very different from this prior notion of zero shot learning that I just described, where your training and testing classes were disjoint, right? Why? Because essentially what CLIP says is that you can simply do image text matching as a pre-training objective on large pool of curated image text pairs. And then at test time, you could come up and bring me a totally different data set, which had a bunch of images and a bunch of classes. And I could just do the image text matching as an inference task, right? Note that you don't actually train on the sort of test sets is the assumption that people had. But the problem is that as these data sets get larger and larger and larger, sort of the term zero shot itself has diffused, right? We don't really have an idea what's in the training set anymore. So we can't really make those claims unless somebody manually inspects these data sets to sort of look at what's in the training set and what is the model actually generalizing to at inference time, right? So that's the broad premise. Hence, given this sort of rough motivation, our goal in the paper was to take a sober look at the zero-shot generalization of multimodal models. So when CLIP says, yeah, we can zero-shot classify these models, and when DALI says we can zero-shot generate a bunch of images, what do we actually mean? What is this zero-shot notion actually being captured in the multimodal models is what we are trying to understand. And the way we operationalize this goal is using two very simple constructs. The first construct is notion of performance, right? So you take the model that's already been pre-trained and you evaluate it on a bunch of downstream tasks that usually you would use, right? So for CLIP, it would be classification and retrieval tasks. And for text to image models, it would simply be some sort of prompts that you would use to generate some images and then sort of look at the FID or some human performance metrics, right? So that's the first construct where we look at model performance. And then we also want to look at this notion of concept frequency, which is essentially you have a bunch of concepts. I'll get to that in a second, how we actually get the concepts. But assuming you have a bunch of concepts, we simply want to measure how often these concepts occur in the pre-training dataset, right? Note that the original OpenAI clip dataset is not public. So we use a bunch of other image text datasets that are public that have been used to replicate the results. And we simply try to quantify the frequency of certain concepts in the pre-training dataset, right? And all we want to do is then look at how does the frequency of these different concepts predict the performance of the model on the same concepts, right? So for instance, I get the frequency of a concept like dog, and then I want to see how well does the model do on the concept of dog. And we do this across a bunch of different concepts and then want to simply plot some scaling laws, right? That's the essential goal of our work. And yeah, the way we conduct this is we have a bunch of these pre-training datasets, as I already mentioned, including CC3M, CC12M, so spanning from 3 million image text pairs all the way up to 400 million. And then we have 27 different downstream datasets where we test them on, like classification, retrieval, and generation. And we have a bunch of models that we test, right? And I mentioned the notion of concept, right, a second ago. And I said I'll get to how we actually disambiguate this. So concepts in our sort of paper are anything and everything that you can think about as nouns or verbs that you would look at in daily life, right? Because our goal in this work is to essentially look at how models perform on certain concepts, the way we collate these concepts is from downstream tasks. So there are a bunch of tasks that people care about when training these models. So we simply go ahead and take all of the downstream tasks that usually people care about and then try and figure out what concepts are actually encapsulated in these data sets, right? So for instance, for classification, we would simply take the class names of the data sets. For retrieval and the text image generation prompts, we would essentially do some sort of pause tagging, lemmatization, and extract all the nouns from the data sets themselves. And then once we have this, we collate all of that into a concept bank, and we have in total about 4,000 concepts from these different downstream tasks. Once we have the concepts, what we want to do is characterize concept frequency, right? But note that because we are working with image text pairs, you can count the frequency both in the image as well as in the text, right? However, remember that the objective of these clip models is to do image text matching. So the way we want to characterize frequency is frequency where a concept is present both in the image and the text in a particular sample. And to do that, we first simply count how many times the concept occurs in the pre-training dataset captions. So we simply construct an inverted index to do this, and we can get a bunch of inverted indices for each concept and the exact sample IDs in the dataset that these occur in. For text, this is very simple, right? You can sort of do exact or regex string matching. For images, this gets a bit more complicated because you kind of have to identify what concepts are actually there in each of these images. So for that, we ran a bunch of different sweeps over detection models, tagging models, etc. And we landed on this model called RAM++, which essentially is able to give you very precise tags for each image, given a bunch of concepts that you feed in, right? And based on this, we again get a bunch of inverted indices where you have concepts and all the samples that contain this concept. And at the end, we have image and text inverted lists, and we can simply take a set intersection, right? And that's how we characterize concept frequency in total. Very simply, we get for each concept the exact number of samples that contain both the concept in both the image and the text, right? And then I'm going to basically show these kinds of plots, as I talked about, like the scaling plots. So let's essentially look at the first plot on the left here, right? And then we can talk about all of the rest. So in each plot, what I'm showing you is on the x-axis, the concept frequency, right? So for each of the 4,000 points, concepts, we would have 1 point exactly on the x-axis, right? And then we can also measure the performance of these clip models on a particular concept, right? So you would essentially get a scatter plot of 4,000 points, where the x-axis is essentially how often does that concept occur in the pre-training data set, and on the y-axis, essentially showing what is the accuracy or performance of that model on the particular concept, right? And then we do this across a bunch of downstream tasks like classification and retrieval. Those are the two rows, and across a bunch of models, which are the individual lines in each of these plots, and across a bunch of data sets, pre-training data sets. Those are the columns, right? And strikingly, in almost all of these cases, you see consistent lines on a log linear plot, right? So this is essentially telling us that model performance is essentially determined by concept frequency log linearly. To break that down even further, this is essentially telling us that if you want to improve performance linearly on the y-axis, you want to improve model performance by a little bit on a particular concept, you have to exponentially increase the number of samples you see for a particular concept, right? And this is essentially showing us a very bleak scaling behavior with respect to data. Um, so this is a consistent log linear scaling trend across all the plots we've seen here. And then we also tried this out for text to image generation models. Again, we see roughly similar trends with a bit more noise. But the noise essentially boils down to the evaluation metric, and we have a bunch more plots in the appendix of the paper where we get much cleaner straight lines on a log linear plot, right? And essentially, we have three key findings from the plot, which I've already said before, but to dial that down further, we have an extremely log linear scaling trend between this concept frequency and zero-shot performance. And essentially, this tells us that if you want to linearly improve performance, you have to scale up your data exponentially on a particular concept. And all of these results are pointing to extremely sample inefficient learning algorithms currently, right? Because if you need exponentially more data, this is kind of a very bleak scaling behavior. And then obviously there are questions about how robust this result is. Are there potential confounders that one could think about? And we controlled for two important confounders. One of them being, as your data set size increases, it's very likely that you could have your test set in your train set, roughly, right? So essentially, sort of, is the trend simply an artifact of your similarity between the pre-training data and the downstream data? So that's one thing we control for. And another thing we control for is we thought about, well, these are natural data sets. What about data sets where people have explicitly curated them to be and sort of like balance them out to have a very non-long tail data distribution? And then we also ran experiments on them. I'll skip the details again of how exactly we did those. You can find that in the paper, but the sort of key result still holds across both our control experiments. So on the left, you see where we control for similarity between the pre-training and the test data set. We see again log linear trends. And similarly on the right, we see the same trends holding for a purely synthetic pre-training data distribution, right? And then beyond showcasing this sort of scaling trend, we had a few interesting data-centric nuggets about just general image text data sets, which we believe can be very useful insights for data curation. So the first one is essentially that across different data sets, all the data sets follow a long-tailed concept distribution. So you see here we plotted three different natural data distributions, and almost all of them follow a long-tail concept distribution where some concepts are extremely highly represented while others are flattened out. And this is true even when you explicitly balance data sets. So there are some data sets like metaclip and synthclip where they do some sort of truncation on the tails to normalize the distribution. However, this still leads to a long tail concept distribution because if you think about it, concepts are repeated, right? Like when you think about concepts in the real world, a lot of them are synonyms and things like that. So you can have a very hierarchical distribution. So even if you actually do a truncation, you are not accounting for this fact. And similarly, the other point is that concepts co-occur, right? So usually you'd have woodpeckers and trees together. So if you truncate woodpeckers, you naturally also truncate sort of the tree distribution. And you can think about when you do this at scale, how that truncation affects the long tail concept distribution. So this has very big, broad implications for data curation in general. The second nugget we found was that we explicitly tried to quantify the misalignment between the image text pairs in a data set. And what we found was that almost all of these data sets have quite large numbers of misaligned image pairs. So where basically the image and the text do not actually match, right? So the image is something else and the text caption totally talks about something else which is not in the image, right? And if you think about this for a second, it kind of is obvious because the way we curate these data sets are from the web, and the captions are nothing but alt texts of these images. And obviously you can think about people who actually write alt text are not really incentivized to write good alt text. And this is a simple explanation for why we see such misalignment degrees. And this is also the reason why recaptioning methods are getting popular these days, where a simple way to improve data quality is to fix the images and simply use a different recaptioner to improve your text captions. And finally, a very interesting thing we found was that the concept frequencies that we found across these different data distributions were all highly correlated. What I mean by that is if you just simply take all of the concepts and accumulate them into vectors, and you take the sort of correlations between these vectors, you would get extremely high values. And what this is telling us is that all the web data that we crawl is different because of the different curation strategies, yet very similar. The web naturally induces a long-tailed concept distribution, which is what our sort of table is showing here. And the best we can think about is to make peace with it and find better curation strategies and truncation strategies, for example. The web by itself is not going to solve its long-tailed characteristics. And this is only going to get exacerbated as we introduce more and more data on the web, right? And finally, the sort of last in the paper was we sort of wanted to foster further research into solving this long-tailed problem, because as we said, we cannot keep having algorithms that are extremely data inefficient. So we curated a test set called Let It Wag, where we curated some images from the least frequent concepts in the Lion 400 million data set. And then we created a classification data set as well as a text-to-image prompting data set out of it. And then we released this such that the community can make progress on this and sort of get closer and closer to solving the issue of long-tailed classification. And to sort of motivate further experiments, we had this plot in the paper where on the y-axis, we look at Let It Wag accuracy of different models. And on the x-axis, we have just standard ImageNet classification accuracy as a reference baseline. And we tested about 40 or 45 different clip models released open source on these data sets. And we see consistently that there's 20% drops from ImageNet accuracy to Let It Wag accuracy. And hence, this is essentially telling us that you want to be making progress both on ImageNet, right? Because that's a standard data set that one would want to look at, but also on this long tail data set that we released called Let It Wag. And effective interventions would essentially try and push closer and closer to the x equal to y line. So that pretty much brings me almost close to the end of my talk. Just to quickly wrap up, some brief insights from essentially the talk. The key takeaways you should be looking at are the web is naturally long-tailed, and there is a lack of high-quality data for all use cases. Hence, the best we can do is make peace with it and sort of try and combat that with smart data curation strategies. The second big takeaway is that from our plots, you can clearly see that current multimodal models are extremely sample inefficient. So if you want to improve performance on a particular concept linearly on the y-axis, you need to have exponentially more data samples, which points to quite a bleak scaling trend. And then there are a bunch more questions that in general we want to be thinking about. that, for example, if you want to do this downstream task of curation, what do you actually want to be generalizing to? For example, if you have a very large data distribution, if you train on everything, there might still be some OOD test sets that one would want to improve performance on, for example, like the let-it wag data set. And hence, improving data set priors is getting traction in the literature these days, and that might be one suitable avenue for improving. And finally, just to end with some open questions and stimulate some food for thought, one thing we haven't really looked at is the effect of model scaling. We did sweep across different model sizes. However, we didn't really do a significance test of how does this scaling slope change with different model sizes, and what does this mean with respect to existing scaling laws in the literature. Another thing that we did not explicitly look at, but now there has been a paper that kind of builds on our work, is talking about compositional generalization, because in our work, we only look at concepts in isolation. So we look at them as atomic units and don't actually look at interactions. But we know that concepts are interacting all the time, right? And that's just the nature of the natural world. What is the effect of compositional generalization? How can we look at scaling trends for compositional generalization? And finally, the sort of gold standard we want to go towards is effective solutions, right? Like, what are effective measures that we can use for curating data and combating the long tail nature, and some specific strategies that might be worth noting to make progress on our retrieval augmentation and some balancing strategies, and maybe some sort of quality filtering. And that brings me to the end. Thank you so much for your attention, and yeah, happy to take questions as and when they come in.
Fantastic. So we'll go ahead and include these links in the follow-up email if you can't zap them with your phone to get the QR codes. We do have one question in the Q&A. Jim F asks, and this was about 5 slides prior to the conclusion of your presentation. Did you see any effects on results of concepts per images or per image?
Yeah, this is a great question. We actually did not, because we did not look at that in too much detail. The way I'm interpreting that question is, what does the sort of concept distribution per image look like? Like, how many images are there? How many concepts are there encapsulated within an image? And if that distribution looks somewhat differently. No, we did not look at that. But like I said, I think this kind of is close to the second point on the slide here, where you want to be thinking about compositional generalization, so sort of interactions of concepts within a particular data sample, rather than simply looking at them as atomic concepts. And yeah, so I think looking at that paper, which I can link to later, would be interesting.
Fantastic. So we do have another question. This one comes from Haresh, who asks, what is the meaning of let it go accuracy in the plot you shared 2 slides ago?
Yes, so I'm interpreting that as let it wag accuracy. So let it wag is the data set we released, which is a long-tailed classification data set. And essentially, the accuracy of different clip models on our data set is the let it wag accuracy. That's on the y-axis, and on the x-axis is just standard ImageNet, right? That you would use. And both of these are zero-shot classification.
And this next question comes from MH10, and I believe it was in response to the answer to your first question. So it means that these large models are overfitted to all those massive amount of training data, I guess. So it means that these large models are overfitted to all the massive amount of training data. They are not actually generalizing to the large amount of downstream tasks, just strictly remembering on the data they were trained on.
Yeah. So I think that's sort of the rough takeaway. I know it's a kind of like a strong claim to make, but I will go out on a limb and say that there is sort of some level of generalization, but it's not the generalization that you would expect. So essentially, what we've been seeing before is, like, when we had ImageNet trained models, there were all of these like domain and distribution shift generalization questions that were coming in, right? Like, if you only train on ImageNet, do you generalize to certain other domains? And people were like, no. And sort of with the arrival of CLIP, people thought we solved those issues, but it turns out there's still a bunch of literature showing that no, these models are really sort of not generalizing well enough to outer distribution cases. And hence, our data set is one in this sort of whole spiel of datasets, but there are also many other works that sort of roughly say the same claim. And so the broad answer is yes, there is some yes, but there is some amount of generalization that you would expect, but not totally.
And we'll take two last questions. The next one is that clip accuracy on long tail balanced data sets?
Yes, yeah, exactly. So that's clip accuracy on the long tail data set. Yeah.
And then our final question here before we move on to our next speaker, how did you use RAM++ to assign concepts? Is there some tuning for thresholds or voting, etc.?
Yeah, a great question. Yes, we do use some thresholding, and we sweep across different thresholds, and we show that our result is actually agnostic of that. So our results hold across different thresholds, and for the main paper, we just use the best threshold we found. But in the appendix, you can find all of these details.